Now that we've gone over our big O notation, we need to analyze our how long each of these operations in I wrote take. How long do each of these things take? Okay? Well, let's start with this one. This one was fairly easy. We've gone over this one enough time. This is a constant time operation over here. Same with checking is it empty. Checking if the size is equal to 0, that's a constant time operation. It doesn't depend on how big the this loop is, on how big the list is. What about the add operation? How long does that take? Well, adding on to the end of an item, that we firstly need to analyze what this is doing. First thing we do is we do an out of bounds check. That's just a simple check. Okay, that's a constant time operation. We're going to ignore it. So now, if the size is equal to the capacity, we have to do this reallocation, which is going to take O of n time, right? We have n items, so we have to move all n items over, right? But that only happens sometimes. So as a result, we say that this is amortized over the cost of adding. Basically, this means that this happens sometimes. In fact, it happens rarely. But if this reallocation algorithm is poor, right? If we do what I told you not to do, if we do right, what I told you not to do in this is that we don't want to make a... Oh, sorry. Where's my reallocate function? Oh, there it is. Right? I told you to do if I tell you, right, this doubles the capacity, which means that now we get to go twice as long without having to reallocate again. Okay? But if we add a +1 capacity, if we were only doing +1, then the add operation, every single time, we'd have to reallocate and shift over n items. So then it would always be an O of n operation. Okay. What about this? The shifting of the items. Well, if adding to the end, this is constant time, as long as we didn't have to reallocate, right? But if we're adding somewhere at the beginning, of course, then we have to shift over. If we're adding our nth+1 item, and we're adding it over to the beginning, then this for loop runs over the entirety of the list. So it takes O of n time, right? We have a single for loop. It's not nested, so it would take the entirety of the list. So this operation takes O of n time if we're adding to the beginning. If we're adding to the end of the list, then it's not going to take any time at all. What about somewhere in the middle? Well, then we're shifting half the list over, n over 2. And so this brings us to the rule number 2. Oh, sorry. No, I forgot to go. Rule number 3. O of n over 2. So rule 3 of this is that we drop all the factors. So n over 2, that becomes O of n time. So if it's somewhere in the middle, it still takes O of n time, right? There's no O of n over 2. There's just O of n. And this is a constant operation. This is a constant operation. So the add operation, right? This is worst case scenario, an O of n operation moving n items, then moving another O of n items, which is 2n. Sorry, moving n items, then moving n items, which is n plus n, which is 2n, which means that this entire operation is O of n. What about remove? Well, we don't have to resize. If we're removing the last item in the list, we don't have to shift everything over. If we're removing the first item, we have to move n items over. So this is an O of n operation, unless we're removing O of n, unless we remove last item in the list. Get and set, though, for get and set, all we're doing is going into the indice, or we're grabbing an index and, right, we're grabbing the item out of the index, or we're taking the item and storing it in there. These operations are constant time because just to get to a location in an array takes constant time, right? Because what the array does is that it uses the memory location and the index, throws it into an equation that takes constant, that's just, it's a multiplication operation it has to figure out, and it gets your item back out, the index of your item back up. So get and set are constant time because it knows exactly where each index is and just can teleport to there and pick that up. What about index of or contains? Well, these are for loops that go over the entire array in the worst case scenario to find that the item isn't there. So it goes over, right? These loops go over every item in the array. So they are O of n, right? One loop, not nested. So these are O of n operations. So what we're now going to learn about is linked lists, right? And here's the fun thing about linked lists, right? We were going over that basically adding an item to the front of a list, right? That we were saying when we have, once we get to a certain time, that takes a while. Adding each item at the beginning of the list, that's an O of n operation, right? So it takes a while, right? This took 2 seconds. And now this can take upwards of 20 seconds to do, essentially. It's going to take a while to do. However, linked lists work completely differently. Linked lists, if I run this, why is it not liking me? Oh, because I have to, right, because I didn't do an array list. I said, here we go, list equal to a new linked list. So let's go ahead and run this now. If I do a linked list over here, it ran in 644 milliseconds. Linked lists are built completely differently, and as a result, we can do completely different operations with them. Or rather, we can do certain operations quicker, but other operations will be slower.